welcome to our final day. Just remind everybody that the abbreviated or shortened program for the day, so talks 9, 10, 11:15, and 12:15. There's tea after the 10 o'clock talk, and then so anyway, all four packed into the morning and action packed, so then I guess dash out for lunch. So anyway, that's, you could all check the schedule, but that's for today. For now, I'm delighted to introduce Lisa Piccirillo, who will tell us about four manifolds with boundary and fundamental group Z.
Thanks, Denny. Yeah, thanks everybody for getting up early on the last day. I'm happy to be here. It's been a really wonderful conference and place to be. I also should take the opportunity to say whatever I want about Tom because he's conspicuously not there, but maybe I'm still at MIT, so I should not do that. And so let me tell you what this talk is going to be about, which it's going to be entirely about some work that's joint with Anthony Conway and Mark Powell. And what we're going to study is some objects which, well, it's sort of not very original. I'm going to try to study a little bit about manifolds and a little bit about knots in them. But the context I'm going to be working in is that the dimension will be 4. And so in order to have a talk that contains me convincing you that we know really anything at all, I need to put some really strong restrictions on what kind of 4 manifolds I'm talking about. So I'm going to assume that pi 1 of either the manifold or the surface is either trivial or Z. So some comments about what knots mean. Dave made a compelling case yesterday that codimension 1 is an interesting place to study knotting, but I'm, again, being less original. Knots will be codimension 2, so you might want to think about this as surfaces. And then just like in classical knot theory, when I talk about the group of a knot, I want to talk about its complement. So all of my surfaces are going to live in simply connected spaces, and when I say the group of the surface, I mean the group of the complement. Okay, and then now what I want to try to do is tell you what we know about these objects in a few categories. So I'll tell you what we know about them topologically, what we know about them for the smooth closed setting, and in the smooth with boundary setting. Topologically, we know quite a lot. I'll state them more precisely, but for these groups, both for 4 manifolds and for surfaces in them, we have classification theorems. And the main theorem that I'm going to talk about today contributes towards this classification. Okay, so we know quite a lot in the topological setting. For the setting with smooth closed manifolds, we also have started to make some progress on the babyest case of this, which is, we've taken kind of the simplest classification problem you can think of, and we've given it a name. So this is the Piccirillo conjecture. And for surfaces, there's something called the unknotting conjecture. And these are apparently hard problems. I'm not going to talk much about them today because I don't have much to say. But what I will talk about is the fact that appropriate analogs of these problems are a lot more approachable if you ask them about smooth manifolds with boundary. So I'll talk a little bit about an analog of the Piccirillo conjecture here, which is known to be false, and an analog of the unknotting conjecture here, which is also known to be false. So this is the plan. Before I get started, let me make one very important disclaimer, which is something you might already know, and it's that other groups exist. And we know a little bit about manifolds with other groups or surfaces with other groups. In the topological category, for example, for finite cyclic groups and something called solvable Baum's-Log solitaire groups, there's some classification work due to people like Hambleton, Craig, Teichner. For surfaces or manifolds, we have some exotica results for other groups as well, but these are the two that we have the most systematic understanding of. So I'm just going to restrict attention to these groups. Great. Any questions before I get going? I'm going to start by, in this category, stating the classifications. Okay. So I'm going to try to state 4 theorems all at the same time because, as you might expect, the classification of manifolds with or without boundary and with one of these two groups looks very similar. So starting with sort of all the attributions, the theorem that you know is that Friedman in 82 gave us this classification of groups of manifolds where, I'm going to start by, talking about the topological category and talking about manifolds. So Friedman classified simply connected closed form manifolds. And a bit later, Boyer classified simply connected manifolds with boundary. For Pi1Z, it's work of Friedman and Quinn. In the setting with no boundary. And the theorem that I'm going to tell you about is a combination of work of my collaborators independently, and then the three of us. We're going to give a classification for Pi1Z and with non-empty boundary. Okay. So the way I'm going to do the statement is that when I need to modify the classification a little bit for the setting where the group is Z, I'll add a modification in green. So the statement is going to be that our set of objects, which is topological form manifolds, let me say with boundary, but I'm allowing the boundary to be the empty set, and Pi1G, where G is one of our two groups. These manifolds, and I'll add a couple hypotheses in a second, these manifolds classified up to homeomorphism, I'm going to say rel boundary. If there's no boundary, that doesn't mean anything. This set of manifolds is in bijection with a set of, in the most generality, 5 invariants. So the statement I'm going to write here is not completely precise. If I really wanted to state this as a sort of precise bijection, I'd need to give you a list of 5 like purely algebraic thingies over here that you can define without referencing the manifolds. That statement's kind of a mess. So the way I'm going to state this now is sort of more intuitively. If you start with a 4 manifold with these properties, what are the pieces of data you need to write down to completely capture the manifolds? But we do also have a realization statement. So if you give me those invariants, then I can give you a manifold. Good. So the invariants, well, the first one is probably something you're expecting. It's the homeomorphism type of the boundary. That's certainly something you need to record. If there is no boundary, there's not a lot of data there. The second thing you need to record is also kind of very simple object. You need to know the inclusion map from Pi1 of the boundary into Pi1 of the filling. Okay? So if you have no boundary, neither of these are very interesting. The first invariant that shows up all the time, you're expecting, you know Friedman's classification is in terms of the intersection form. So that is indeed what you want in the setting with no fundamental group. If you have fundamental group, you want a modification of this called the equivariant intersection form, which I'll describe in just a moment. The fourth invariant is going to be kind of the most mysterious one. I think most people here won't have seen it before. It's something we're calling the automorphism invariant. I'll describe that as well in just a second. This invariant also doesn't exist in the no boundary setting. And then the final invariant is a classical thing called the Kirby-Sieberman invariant. Really loosely speaking, sort of topologically, you can think of this as measuring whether the manifold has a smooth structure. So this is the shape of all of the theorems. If you have no boundary, you really just see these two invariants. If you have no fundamental group, then there's no data here either. So Boyer would maybe just have 4, and we have 5 bits of data. Any questions about this statement? Yeah, Marco?
The boundary is not empty to assume that it's connection.
Yes. Yes, we do. But then, oh. Yeah, we do for simplicity, yeah. I think you could get away from that. Okay, there's a couple of hypotheses that I need to add here. One of them is that I want to be working with boundary a rational homology sphere or some appropriate analog of that. So H1 of the boundary of X, it needs to be torsion. A bit different if when pi1 is z, I'll explain that. And I also want to know that the inclusion map from pi1 of the boundary into pi1 of the manifold is surjective. Okay. So the first things I want to do is tell you what these things are. Any more questions before I start that? So what you're familiar with is the plain old intersection form, which pairs elements of H2 and spits integers. And, you know, generally I think of this as this form that tells you kind of what is the H2 of the manifold and how does it interact with itself. That's an invariant you can define for manifolds with pi1z as well. But it doesn't quite capture everything you need to know, because if you have interesting pi1, you might also want to record how does the H2 of the manifold interact with the pi1. And a really elegant way to capture that is instead of looking at the homology of the space, you can look at the homology of the universal cover, or in this case, the infinite cyclic cover. So the equivariant form pairs these homology groups, and it's going to spit Laurent polynomials. And I'll tell you in just a second exactly what it does, but before I do, let me maybe get a running example going. So maybe you want to think about your manifold as being S1 times B3 for starters. So I'm imagining this tube is, there's an S1 like this. I haven't identified the ends, but you can. And then I want to attach a 2 handle to this, maybe like this. So this is a perfectly nice, very simple 4 manifold with pi1z. And to compute its equivariant intersection form, we'll need to look at the cover. So that's also very easy to understand. We see R times B3. And it now has a whole bunch of 2 handles stuck to it. And they happen to become 3-framed, but you shouldn't worry about that. Okay. So okay, let me now tell you exactly what this form does. Just like the regular intersection form asks how do surfaces representing the classes intersect, we're going to do the same thing. So if you have a pair of classes, let's say represented by sigma and gamma, well, again, you want to ask how sigma intersects, in this case, not just gamma, but all of the translates of gamma. So right, we'll see a sum. So in this case, Well, at first, if you sort of look at the homology of this cover, as a module over Z, it looks infinitely generated. I don't like to write down forms over infinitely generated modules. So you want to think about this, in fact, as being a ZTT inverse module. At which point it becomes finitely generated. Let's say it's generated by like this two handle here. And then, well, okay, we just have to ask ourselves, if I take a class running once over this handle, how does it interact with itself? So we'll see self-intersection 3 from the framing, but then we also have to record how does this class intersect this? And we see a -1 from the linking. And then if I is larger than 1, well, we don't have any intersections between these. For I -1, we get a T, and that's it. So this is what the equivariant form looks like in this case. Questions?
Is the module always free over the boundaries not empty?
If the boundary is not empty, yeah. Okay. So the other sort of more interesting invariant on this list is the automorphism invariant. And to tell you sort of geometrically what this is measuring, let me remind you that when you have this H1 torsion hypothesis that we have, there's a short exact sequence, which looks like this. This is what you see in that simply connected case. So this should be very familiar. And if you're working with a manifold with pi1z, you sort of also have a sequence like this on the covers. And what the automorphism invariant is doing, morally, is capturing this map right here. So sort of in a picture, if you have your boundary manifold and you have some H1 class in there, well, what the automorphism invariant is telling you is which relative class should it be the boundary of. I'm not going to say anything more precise about what this invariant is. You can make it precise algebraically. Let me just sort of try to say something about why you should be expecting to need to record something like this. So if you think about maybe trying to prove the surge activity result here, somebody's going to give you some data, and you're going to need to build them a 4 manifold with boundary and pi1z. Well, as you can sort of imagine what data you're going to want to be told. So you have to have pi1z. They're going to tell you what you want the boundary manifold to be. But we know that there's a relationship between pi1 of the boundary manifold and pi1 of the filling. So you have to ask them, like, don't just tell me the boundary, tell me what that relationship should be. And that's this right here. Okay? And then the next thing they specify is what they want the H2 to be. Now it should interact with itself. That's great. That's this. But then, there's a relationship between H1 of the boundary and H2 of the filling, and that's what the automorphism invariant is asking you to record. Questions here? So I want to sketch how the proof of this result goes in the surge activity setting. The breakdown here is that we proved surge activity. My collaborators had proved injectivity a bit before. And the proof is the outline is very straightforward. It follows sort of in 4 steps. So the first step is just to begin with the boundary that has been insisted upon. So start with M cross I. And then what you want to do is you want to attach 2 handles to it in a way sort of that's instructed by the intersection form, the equivariant form, and the automorphism invariant. Like, somebody has insisted on what the H2 should be and how it should line up with the boundary, and you're just going to force that by putting 2 handles here in sort of the way that you were told to do it. A couple of comments about this. This, so far, what we've built is smooth. And this step here is the main technical work. Once you've attached all your 2 handles, you sort of have some new M prime. And, well, what you have to show is that the homology of the cover of this upper boundary, sort of the one that is associated to the inclusion map on pi 1 down here, the cover of this is has no H1 as a ZTT inverse module. So we have this hypothesis here where sort of H1 of the boundary was torsion. That's something like being a rational homology sphere. And what you show here is that after you finish adding your 2 handles, what you get is something like an analog of being an integer homology sphere. And the reason you want to know that is because you can show that such a manifold, such an M prime, bounds a topological homotopy S1. Okay, so this step here is where the proof is just topological. So this maybe seems very strong and very surprising, but in fact, you already know a theorem like this. In the simply connected case, you know that Friedman proved that integer homology spheres all bound contractible. So this is a pi 1z analog of that. Okay, good. So once you have a homotopy S1 filling of M prime, you can stick it up here and define this whole thing to be your X. And finally, you just verify that X has the right invariance. Yeah.
So you stated that by injection for pi 1 of X equal any G, right?
No, sorry. G is one of my 2 permitted groups here. That would be a really great theorem that we definitely did not prove. More questions? Yeah. Oh, sorry. Where does the restriction that H1 of boundary is torsion come in? I mean, in fact, a few places you, but maybe one that you can see is that this sequence wouldn't necessarily be short without it. But it also, you want it to get a little bit of control over what the equivariant form can be as well. Boyer, by the way, does not need it. His theorem, he can remove it, and the theorem will look very different, but he can remove it. We did not pursue removing it. So this is what I wanted to say about manifolds. I'm going to move on to talking about surfaces. Anything lingering before? So then again, I'll start in the topological category. And here, as I said in the beginning, we again have classification theorems. So Boyer's work gives a classification of, oh, sorry, let me give a whole bunch of setup before I get going. So the settings we're always going to be working in when I talk about surfaces is that X is going to be a topological manifold with pi 1 trivial. The boundary of X is either going to be empty or S3. All of my surfaces are going to be proper. And what I'm going to use for an equivalence here is that I'm going to say that in either category, a pair of surfaces are the same if there's a homeomorphism or diffeomorphism of pairs. You can, there are results about everything I'll say in this section if instead you say isotopy, but it's a bit messier. And then the groups we're really interested in are the not groups. And again, that's not going to be everything. It's going to be either one or Z. Okay. So now in this context, we have some classifications. So Boyer gives us a classification when pi 1 of the complement is 1 and the surface is closed. And our work gives a classification when pi 1 of the complement is Z and the surface can have boundary or not. And I'm not going to state the whole classification here. It looks rather similar to this. So let me just say that classifications exist. A comment is that it's not written down in the literature for simply connected complements for surfaces with boundary, but it's recoverable from this. So in the smooth category for surfaces, there's this motivating conjecture, which is called the unknotting conjecture. And what the unknotting conjecture says is that there is supposed to be a unique S2 in S4 with pi 1Z. So in the topological category, this is a theorem for most genera. So Friedman proved this for genus 0 surfaces, and Conway and Powell proved this for genus greater than 2. Before you ask, it's open in genus 1 and 2. It's probably true, but their techniques kind of break down. So this conjecture appears to be rather difficult for closed surfaces, but let me try to tell you a little bit about what we do and don't know about them. So and before I do that, let me make a definition. We'll say that a surface is exotic if there exists another surface which is topologically but not smoothly equivalent to it. So you can ask, a knotting conjecture is asking, is there an exotic pi1z sphere in S4? And what we know is that there exist exotic surfaces in some closed form manifolds with pi1z, sorry, with no pi1, that's work of Finn, Tuchel, and Stern. And it's work of Kim and Ruberman with pi1z. And we don't have, so the knotting conjecture wants you to find exotic surfaces in the simplest manifolds you can work in. We're not great at finding exotic surfaces in particularly simple manifolds, but there is sort of one very good thing that we can do, which is this work of Hoffman and Sanuccian, which says there are exotic surfaces in the trivial homology class in some manifolds. And this is important because if you're going to try to produce exotic surfaces in S4, then they're certainly going to have to live in the trivial class. Yeah. They are genus 1. Yeah. I think that there are genus G surfaces in some big manifolds. In particular, exotic genus 0 surfaces in bigger manifolds. In particular, in certain exotic manifolds stabilized with S2 times S2. Okay. But there's sort of still a lot we don't know here. So we don't know whether there exists exotic in S4 of any genus. We don't know whether there is, for example, an exotic CP1 in CP2. So this is sort of a pi1z setting. This is a no pi1 setting. And we also don't know, like, I don't know, more globally, like, if you're given some random 4 manifold, can you find an exotic closed surface? So these problems are, especially these, apparently very hard for closed surfaces, but something that happens a lot, or sort of a common theme for smooth manifolds is that if you work with boundary, things get easier. So what I want to do with the rest of the time is tell you that we know answers to questions like these for smooth manifolds with boundary, and try to sketch a proof there. Questions before I do? Okay. The main result that I sort of want to tell you, and in fact it's the result that I'll sketch, is this really wonderful work of Kyle Hayden in 2019, and he showed that there exist exotic D2 embedded in B4 with pi1z. And he doesn't write it down, but his work also shows that there are exotic D2 in punctured CP2 with no pi1. So that's kind of an answer to these two questions in the setting where you have boundary. And with Mark and Anthony, we answered sort of a version of this question in the setting with boundary. So let's say for any two-handle body X with S3 boundary, there exists exotic D2 in X. And all of these theorems can also be sort of kicked up to surfaces of any genus. This is kind of the simplest case. So for the rest of the time, I want to outline, in fact, a proof of Kyle's result. Our proof relies on what Kyle does, and then you sort of need to do more. But the techniques Kyle uses are, I think, really beautiful and also sort of very common in the literature about exotic manifolds or surfaces with boundaries. So let me sort of try to give you a flavor of what that looks like. Questions before I do? So let me start off by reminding you of a couple of facts. This notation, a dotted circle, this is used to denote S1 times B3. And if we have a dotted circle and let me just say 0 frame 2 handle, linking it as the Hopf link, well, this is B4. And the boundary of this is exactly the 0 surgery on this Hopf link, which is S3, as you know. So you know this, but Kyle's argument is really just this sort of beautiful little trick with this sort of very standard stuff. So Kyle's argument is very straightforward. What we need to do is, one, build a pair of disks. With pi1z. And such that they are topologically equivalent. And then we're going to show that their complements are not diffeomorphic. And this will in particular show that there can have been a diffeomorphism of pairs, and so they can't be smoothly equivalent. So I'm gonna build some disks for you explicitly. Let me start off by drawing a picture. So what we have here is a 4-manifold built out of a 1-handle and a 2-handle. And well, I've drawn a circle in it, and I'll explain that in a second. If you squint at this picture, you'll see that while it looks messy right now, in fact, the 1 and 2 handle can be isotoped just to look like this. So this is really just a picture of the 4-ball. So this green curve that I've drawn, that's some knot in S3. And in fact, we can see in this picture that knot in S3 bounds a disk in the 4-ball, because you can just take this little disk and push it a bit below the 2-handle. So there's some disk here. So in fact, instead of thinking about this as a knot, let's think about it as a disk. And well, well, let me leave it like that for a moment. So this is going to be one of our disks, D. To describe the other disk, let me again draw a picture quickly. Yeah. I'll ask you that question in a second. Okay, so this should look like exactly the same picture I had before. And again, I'm going to think of it as a 0 and a 1 handle, but I'm going to order them in the other direction. Because in your head you checked that this was a hop link before, I'm allowed to put the dot and the 0 in the other order. And that will again give me some sort of convoluted looking diagram of the 4-ball. So again, this green curve, this is some knot in the boundary of the 4-ball. And in fact, it's exactly the same knot as we had before, right? Because the boundary of this 4-ball is like bang on identified with the boundary of this 4-ball. They have exactly the same surgery diagram. So these are the same 2 knots. Okay? And then something that's a little bit less obvious in this picture, but still true, is that this knot here in sort of this 4-ball, this also bounds a disk. And the way you see that is that if you close this up right here, you would be able to drag the 2 handle around so that this only had intersections with the 2 handle, and then it'd be able to bound a disk for the same reason this does. Okay. Great. So this is this pair of disks in the 4-ball. They have the same boundary, and it's not too difficult to check that indeed their complements have pi 1z. We know how to describe their complements. It's actually just to think of these as themselves dotted circles. And well, in this case, for example, you can then just read off pi 1, and it turns out to be z. So these are these 2 disks. They have the same boundary. They're both in the 4-ball. They both have pi 1z. And then you can just appeal to the classification to decide that they are indeed topologically equivalent. So let me break for questions there about the construction. So 2. Now I just have to show that these complements here, which are in fact the manifolds whose handle diagrams are drawn here, I just have to show that these are not diffeomorphic. The first thing you want to observe, and this is something you can just sort of check using Snappy because we know a whole lot about 3 manifolds, you check that the mapping class group of the boundary of, well, either of these surface complements, check that this is trivial. So what this tells me is that if I did have a diffeomorphism, well, it would have to restrict to only this. It would have to restrict to this one map on the boundary. And in fact, I can reasonably call this map the identity map because I have this exactly the same surgery diagram of these 2 boundaries. So schematically, what we see going on here is that if we had a diffeomorphism, well, on the boundary, it would have to be the identity. Good. Okay. So what that tells me is that if I had some homology class in the boundary, then I could take slightly bigger manifolds, which are built by attaching two handles along that homology class. Let's say this is W and this is W prime. And these would be diffeomorphic because I can just use the identity map on the handles. Okay. So this seems a little bit gnarly, like we wanted to show that these manifolds weren't diffeomorphic, and what I've done here is I've made them bigger. That maybe seems unnecessary, but what's really great about this step is that these manifolds now have some H2 if you add enough two handles. And in particular, maybe you want to add two handles here and here. And now, as Andras told you the other day, the genus function steps in as a really great way of showing that these manifolds aren't diffeomorphic. So, for example, you can ask, let's say, sort of any constructive four-manifold topologist to show you that there's a sphere-generating homology here. And you can ask Paolo to show you that there's not a -1 sphere-generating homology here. So I'm going to stop with this. This is this sort of very classic argument, and ours is kind of an extension of this. Thanks.
Questions for Lisa?
Yeah.
I'm a little confused. Can you explain a little better the picture? So you on the left and on the right, you have the two is complements.
Yeah.
Yeah. And so what do you mean by is the identity on the boundary? Those are two different manifolds.
Well, I guess I mean, I have surgery diagrams of both disk complements, which are literally the same as surgery diagrams. So if you feel very strongly that I not call it the identity, that's fine. I'll call it the pointwise fix map on this surgery diagram of the boundary. Yeah.
I feel like maybe you answered this, but what's your answer to other Paolo's question about why you do these steps?
Yeah, it's because, oh, sorry, I'm supposed to repeat the question. Why did I draw this looking like a front projection? And the reason is because for once you've added some two handles to this disk complement, it's easy to check that this is a Stein manifold, and therefore it's not allowed to have a -1 sphere.
Can you give us like a hint as to where this picture came from?
Yeah, I guess it's just kind of an augmentation of the standard Maser cork. Maybe we need to get a little more creative in this field, but something we use all the time to produce exotica is this little contractible guy. And you know what Kyle has essentially done is said, instead of this clasp, I'll think about kind of removing my disk right there. Now you don't want to use this because it turns out not to have pi1z, and it also has the mapping class group of this complement once you appropriately surgery is not trivial, but then you just wiggle this example to try to have pi1z and trivial mapping class group, and that's a solution. Yeah. Yeah. So the question is, how do you improve this argument to prove the more general theorem for any two-handle body? So what you do is you start with a handle diagram of your two-handle body. And then off to the side, you just drill out a trivial disk for the unknot. And now what I'm going to try to do is modify that picture until I have something where I have more than one disk. So the first thing you do is you kind of start running the two handles through that trivial one handle to sort of set up whatever algebraic topology you're looking for. And then you try to get a picture that looks relatively Stein from that by also adding some stuff which has large TB but doesn't contribute to anything else. And then maybe you use a trick like Kyle's to add something where you have a pair of disks, and then an argument like this goes.